Say, welcome to my talk.
Talk?
Say, welcome to my talk.
Welcome to talk.
Hello and welcome to my talk. So, I'm here to talk to you about
Hey, let me
data-driven.
do it. Hey, let me do it.
I'm here to talk to you about data-driven methods for higher order dynamical systems. We're going to develop a new kind of Hilbert space, and we're going to develop new kinds of operators that are made to handle non-local information. This is work that I'm doing with Rishikesh Kamalapurkar and Benjamin P. Russo. Now, I would like to thank the organizers of SEAM for inviting me to give this semi-plenary talk, and I hope all of you are doing well. I don't know how it's been for you guys during this pandemic, but personally, I've been locked in the house with my twin toddlers for the past year. And you know, it's fine. Everything is fine! Here, would you like to hold this?
No, not that one.
Oh, look, there you go.
I can't push that one.
Okay, yeah, push that one. So I've organized this talk to start with data-driven methods for discrete time dynamical systems using Koopman operators. These are composition operators, and this is how most people do this sort of data-driven modeling using a method called dynamic mode decomposition. My colleagues and I have been working to extend a lot of these ideas past just discrete time dynamical systems to proper and true continuous time systems. So we've looked at things like Liouville operators and introduced ideas of occupation kernels. And this has added a tremendous amount of flexibility to these data-driven methods for dynamic mode decomposition. And so this includes things like control Liouville operators and control occupation kernels, where we can now do dynamic mode decompositions of control affine systems. And the work that I'm showing you today demonstrates how you can effectively leverage a lot of these same ideas for higher order dynamical systems in a way that will allow you to avoid doing a lot of numerical differentiation, which is really how it's done nowadays. And a lot of these same ideas employ non-local operators, and so they're readily...
I see a mouse.
Yeah. And so they're readily employed for fractional order systems too. Now we have a whole...
See operator.
Operators.
Okay.
So a lot of these ideas can be extended readily to fractional order dynamical systems. And we have a whole other framework actually that we made just for that. But it would all fit into this discussion here as well. Today I'm going to focus on second order dynamical systems primarily, just because you can get a really nice clean representation for it. But a lot of these methods, like I said, apply for fractional order systems, third order systems, fourth order systems. And the really neat thing is that even though we have built up a huge framework for these operators and for the study, computationally, it works out almost identical to the Koopman operator case, if you look at it right. Understandably, I've been recording this piecemeal over the past week because, well, children are a lot to manage. And so why don't we go ahead and jump into it.
Let's do it.
All right.
What did you say your name was?
I am Dr. Joel A. Rosenfeld. I want to talk to you about data-driven methods in dynamical systems, and in particular, I want to talk to you about the interplay between some new Hilbert spaces that my colleagues and I have developed, as well as operators that are inherently non-local. We're going to use these in order to analyze data that we've collected from some sort of higher order dynamical systems, and we're going to show how to build a model for this system straight from what we call their snapshots. So why don't we go ahead and get started. So if you've seen any of my previous talks, you know that you can use the Koopman operator in order to sort of model a discrete time system. You're collecting data in the form of what are called snapshots. This could be a collection of stills from a video. It can be photographs, like in Roger Rabbit with the pictures of patty cake. And it could also be a collection of snapshots from a fluid dynamical system. This one here is the one that corresponds to flow around a cylinder. Now the idea is that we treat each of these as a discrete time dynamical system, and we can use kernel functions and composition operators, which are also called Koopman operators, in order to build a model for the system. Problem is, we don't know exactly what the discrete time dynamics are. This is a data-driven problem, so we don't know the dynamics, but we'd like to discover them. So what we're going to do is we are going to build a finite rank representation interpolation based on the snapshots we've seen of the composition operator, the Koopman operator that represents the discrete time dynamics. And then using this, we can build the eigenfunctions for this finite rank operator, and we'll just sort of assume that they're close enough to the eigenfunctions of the original operator in order to build a model. We can use the eigenfunction equation or this composition operator in order to show that the eigenfunctions themselves, when they're acting on a snapshot, just become lambda to the I+1 of the eigenfunction applied to the initial x0. Then we use these eigenfunctions to approximate what we call the full state observable, or really the identity function. And then we feed into that identity function the current snapshot, and then throughout we have a model for this dynamical system using these eigenfunctions. We have a whole bunch of pictures of an unknown discrete time dynamical system. Instead of trying to figure out what the dynamical system is directly, we use a Koopman operator that acts on observables. It advances a snapshot within the observables themselves. The reason why we want this is because if we find eigenfunctions of this operator, if you take the eigenfunction and you evaluate it at a snapshot, then it is really just lambda to the n times phi of x0. So we're going to use kernel functions in order to figure it out. The adjoint of the Koopman operator on a kernel function advances the center of the kernel function from x to f of x. So then we come up with an operator level interpolation of the adjoint of the Koopman operator. This gives us a finite rank representation of the Koopman operator's adjoint. Take the transpose, take the eigen decomposition of that, and use those as our proxy eigenfunctions for our Koopman operator. Now you use these to decompose the full state observable, and you have a model for your dynamical system. If you need this for all of Rn, then you do this for each dimension, and that gives you the Koopman modes. In a couple of weeks, we're going to really start talking about this in my class, and so subscribe to learn more. Now, of course, since we really care about the vector output of this model, you really should consider vector-valued reproduced kernel Hilbert spaces, and we'll get into those in a minute. But if we just stack them like what we did, this is really equivalent to doing a vector-valued reproducing kernel Hilbert space, where the vector-valued kernel or the operator-valued kernel is really just a diagonal of the same kernel all the way down. Now, if you have been following my talks, then you know I have a little bit of a vendetta against the Koopman operator in particular. Now, before I get into my criticism of the Koopman operator, I would like to stress that these techniques actually work really, really well. And you can get very good reconstruction of your system from these snapshots and actually get very, very good prediction. So the fundamental problem with Koopman operators really happens at the level of dynamical systems. So all of these systems that we care about modeling and extracting dynamics from, these are usually continuous time systems. And the way you get a discrete time system out of them is by fixing a time step and doing an integration. So this will lead us to a discrete time dynamical system that comes from our continuous time system. But the issue here is that not every continuous time system is actually discretizable. Even at the quadratic level, you have x dot is equal to 1 plus x squared, where we know the solution to that is going to be tangent of some kind. And we know tangent functions have finite escape time. And so that means that you can't come up with this discrete time dynamical system because there's going to be points where you have holes in them. And we need the domain of discrete time dynamics to be the entire plane, or all of Rn. Another problem that comes up is that there aren't actually a whole lot of bounded Koopman operators or composition operators for a given reproduced kernel Hilbert space. For instance, I mean, everybody here knows that the Fock space has only affine bounded composition operators, and in fact, if you want them to be compact, then you need the A term to be magnitude less than 1. And I mean, if you're looking at this sort of data-driven methods, you're usually thinking of things that are going to be nonlinear. The whole idea of casting this to an operator is that you want to change a nonlinear dynamical system into a linear operator where you can do eigen expansions and spectral methods. So my colleagues and I have been pushing this whole idea of using what are called Liouville operators. Now, these Liouville operators arise from what we call the orbital derivative. So basically, if you have some sort of dynamic, say x dot is equal to f of x, then you make this operator as being a sub f acting on some g as being formally written as the gradient of g times f. Now, if you take a trajectory that corresponds to this dynamical system and you look at it from, say, 0 to, say, capital T, if you plug that into this operator, this will ultimately end up being just the time derivative of g composed with gamma of t. And so then you can use an integration from, say, 0 to t in order to extract some information out of it. And so we know that that integral then would end up giving you g of gamma of big T minus g of gamma of 0. That right-hand side can be written as g inner product with a difference of two kernels centered at gamma of t and gamma of 0, respectively. Now, what do we do about the other side? Well, it turns out that there's a really slick thing that we can do, and we can introduce these things called occupation kernels. Now, occupation kernels are these things that sort of represent integration along a trajectory from, say, some finite time, so 0 to 1, and you end up getting a bounded linear functional, which means that there is some function inside your Hilbert space that represents this. And we call these the occupation kernel corresponding to the trajectory gamma. So then today you have the occupation kernel corresponding to a trajectory is actually in the adjoint of an operator, assuming it's densely defined and closed. And then the mapping of the adjoint on this occupation kernel is a difference of two kernel functions. So this ends up being a little bit more complicated than what you face with the Koopman operator, but at least you don't have to discretize the dynamics. So then the question becomes, what do we do about compactness? And this is something I've been working on with Benjamin Russo, Rishikesh Kamalapurkar, and my graduate student Himanshu Singh. And so what you do in order to get a compact operator is that you end up precomposing with a composition operator before you apply the Liouville operator. And we call these Liouville weighted composition operators. When Rushi and I first introduced these in this paper here, along with my wife, L. Forrest Groos Rosenfeld, and my former postdoctoral advisor, Taylor T. Johnson, we can end up finding a bounded and compact operator. And what's really significant here is that you don't end up changing the trajectories all that much through this adjoint relation. And so that the finite rank representations that we end up making at the end of the day to represent this Liouville weighted composition operator, they're going to be really, really close to the same finite rank representations that we end up making for the Liouville operator. And in particular, even get that to be within machine precision. And we see that for the Liouville operator, if we take an eigenfunction and we compose it with a trajectory, the ultimate result ends up being e to the lambda t times that eigenfunction evaluated at the initial point for the trajectory. And so then we can do the same sort of deconstruction we did before for the full state observable, and then we can build up a model for our system. So this achieves exactly what we had before with Koopman operators, but now we're getting it for a continuous time system directly by avoiding this whole composition operator and snapshot approach. But we'd like to take this a little bit further, and there's other problems with the dynamical systems and the way that they're approached that we'd still like to address. And one of these things comes from numerical differentiation. Numerical differentiation is, of course, something that people are going to be using in order to get at data-driven methods for dynamical systems, because a lot of your systems are differential systems, and you need to take derivatives in order to get estimates of your dynamics at a particular point. And so you can do fitting methods and other things like that, and this is what the Cindy algorithm does by Nathan Kutz and Steve Brutton. And their method works fantastic. They use these sort of compressive sensing approaches and a huge library of functions to fit dynamics to. But one of the things that they run into is that they have to do a lot of filtering to the numerical derivatives that they take in order to get some feasible signal out of it. And this can work, especially for first order derivatives. But once you try to go past the first derivative and to the second derivative, even the third derivative, you run into big trouble. So here what we would like to do is we'd like to move away from taking numerical derivatives and moving to something else that's a little more stable. So how do we approach these higher order dynamical systems from a data-driven standpoint? So we could stick with the continuous time Liouville operator dynamical mode decomposition that we just came up with, and there is a path forward. What you would do is you would basically augment your state variable. So you have some dynamics, say x double dot is equal to f of x, and we can convert this into a first order method where basically you augment your state variable with x dot. So you replace x with z, where z is equal to x and x dot. And so then when you take the derivative, the time derivative of z, you end up getting x dot and x double dot. And so then through this you have converted your second order dynamical system into a first order dynamical system. But when you're looking at this from a data perspective, what you end up saying is that you only have the data for x, and so then you need to come up with an entire trajectory for x dot. And so that involves taking a lot of numerical derivatives, and we want to avoid that as much as possible. And when you get to a third order system or a fourth order system, you're going to have to do that over and over and over again, and that's going to give you really, really noisy data. And so we would like to take that the opposite direction. And so what I'm going to do now is I'm going to tell you how you can sort of go in reverse and use integrals and say second order integrals in order to avoid using any of these numerical derivatives. But what we're going to have to do is we're going to have to do a little bit of operator theory. We're going to have to define new occupation kernels, and we're going to need to define some new Hilbert spaces. So let's go ahead and get into that. Okay, so we'd like to take this whole operator theory approach to higher order dynamical systems. And why don't we focus on second order just for this example. So what we're going to do is we're going to develop a new operator, and the way we do this is we follow the same inspiration that led us to the Liouville operator, and that is orbital derivatives. So we're going to take some function in a Hilbert space, and we're going to compose it with gamma, which corresponds to our second order dynamical system. And then what we do is we take two time derivatives of this composition. So what we're going to get after taking these two derivatives is something that is quadratic in terms of the derivatives of the trajectory, and this is going to surround the Hessian of the function that we composed with. And we're going to have an addition of a term of the gradient of that function times the dynamics. This gives us sort of an inspiration of what our operator should look like, except we have one problem. We have the derivative of our trajectory, and we didn't want to take numerical derivatives. So in order to remove that, we go ahead and change that to an integral, but then we have a new problem, and we can't just plug in x where we have our trajectory, which is what we did with the Liouville operator. And so we're actually going to need the entire history of our trajectory back to when it started. This leads us to something that is called a signal-valued reproducing kernel Hilbert space. And this is going to build on a vector-valued reproducing kernel Hilbert space concept.
This would be a good time to turn invisible.
Yep.
Okay, not going to turn invisible. Selecting a bagel. Act super normal.
Spider-Man?
You know, that's funny. I get that a lot.
Hey.
So vector-valued reproducing kernel Hilbert spaces are more or less just like a regular reproducing kernel Hilbert space. With a regular reproducing kernel Hilbert space, you have that every evaluation functional is bounded, and that gives you a kernel function by the Riesz representation theorem. So for a vector-valued reproducing kernel Hilbert space, you're actually mapping to a Hilbert space rather than just a bunch of scalars. So if you want to get back down to a bounded linear functional, you're going to have to follow function evaluation by an inner product in this new Hilbert space you have. And then that gives you your functional for basically finding your new kind of kernel. So if you take any sort of x in your set X and v in your Hilbert space Y, then you say a space H is a reproducible kernel Hilbert space if it's a Hilbert space of functions from a set X to a Hilbert space Y, such that the evaluation functional of f of x inner product with v for some v and y is bounded, and that's what gets you your kernel functions. Now it turns out these kernel functions, they depend on x and y, but they can be seen as being linear on x. So you can just go ahead and rewrite this as case of x, where case of x is an operator acting on some v. So in our case, x is a collection of continuous signals. You know, they could be, say, n times differentiable or d times differentiable, whatever you like. And we are going to be mapping to a Sobolev space of a single variable. And so we're looking for functions that take continuous signals to continuous signals, and we're going to make this a vector-valued reproducible kernel Hilbert space. Now, how can you find a space that's going to end up doing this for you? What you can do is you can actually take a reproducible kernel Hilbert space that consists of, say, differentiable functions, and you can go ahead and take a signal that you get out of x, and you call it theta. You throw it into a function from this Hilbert space, say g, and then g composed with theta is a perfectly well-defined continuous signal. And so, there you go. Now we just need to put a Hilbert space veneer on this, and we're good to go. And so we basically say that this is going to be our signal-valued reproducible kernel Hilbert space, and we're going to have this canonical mapping from this reproducing kernel Hilbert space that we had to this signal-valued reproducible kernel Hilbert space, and this is just going to basically be the mapping that takes a function of g of x to a function, we'll say phi of g, that maps x to y, just like what we were saying before. And so through this canonical mapping, we can define a single-valued reproducible kernel Hilbert space. We can give it an inner product pretty naturally, and it turns out that that's the entire space. It's actually just a one-to-one mapping with a regular reproducible kernel Hilbert space. But we have now this new way of looking at it as a signal-valued space, which is going to help us when we're trying to evaluate this second order Liouville operator. Now, something that's interesting is that we actually have two different kernels floating around. We have the kernels for the cell space, and we also have the kernels for the original reproducing kernel helper space. And then, of course, we have the kernels for the signal valued reproducing kernel helper space. And so it turns out that for any computational routine that we need to do for this, you don't need the Sobolev space to reproduce a kernel. In fact, you don't even need to reference the Sobolev space at all. You just need it to be there to have a theoretical guarantee. And so you can actually replace the Sobolev space with any sort of single variable reproduce kernel helper space, and that's not actually going to impact the actual implementation of this at all. The things that will impact the implementation and will make a difference is the underlying Hilbert space that you're applying the canonical mapping to. That is actually what the kernel that's going to end up being evaluated most of the time. Generally speaking, it's probably a good idea to pick that to be a nice universal kernel, something like the Gaussian radial basis function or the exponential dot product kernel. And both of these would end up working fairly well at a sort of data-driven context. So now we have a way of defining a second order Liouville operator. And this is mapping from a function acting on continuous signals to another function mapping continuous signals. And so we can define this on a continuous signal by, say, b sub f acting on, say, psi of theta of t, and we define it with this relation here. So that gives us a well-defined operator, and for the right choice of f, you can show that this is going to be densely defined. And in fact, it's also closed. So then companion to this operator, we want to introduce a new kind of occupation kernel so that we can do the same sort of inversion that we did before. And so we're going to basically want to be inverting a second order time derivative. And so we need to define an occupation kernel that is going to integrate twice. And we can define this very easily using Cauchy's formula for iterated integrals. And you have to use a combination of the image space and also the reproduced kernel helper space we started with, but ends up giving us a well-defined bounded linear functional. And at the end of the day, it's more or less what you would expect it to be. So now when we take this second order Liouville operator acting on a function g, and we take the inner product with this new occupation kernel, you end up getting this nice relation. So you see that it becomes the g inner product with this difference of kernels that also involves a derivative of kernel from the image space, which was our Sobolev space. And this gives us something to work with to make a finite rank representation of this operator. So we can go ahead and take a collection of trajectories that all satisfy the second order dynamics, and we can build up a finite rank operator that represents the adjoint of the second order Liouville operator. And so then through the same routine, we can look for eigenfunctions of this finite rank operator and try to do some sort of spectral method. Now, what do you get when you take a look at an eigenfunction for the second order Liouville operator? Well, the same sort of thing as before. If we go ahead and we compose with a trajectory from our system and we take the second order time derivative, you can end up getting this relation. And so it's similar to what you would see with the regular Liouville operator. And so ultimately we want to get a whole bunch of approximations of these eigenfunctions, from our finite rank operator, and then we're going to decompose the identity function again. And this will give us a model for our second order system. Now, you can do this for third order and fourth order systems, and you just have to introduce more occupation kernels that are higher order. If all you're after are these finite rank representations, you don't even have to build the proper operator itself. You just have to know what it does when you take its adjoint and you act on an occupation kernel. And then that can give you these finite rank representations, and then just a little bit of differential equations will tell you what the eigenfunctions would have to do. And so you don't have to go through the whole rigmarole in defining higher and higher order Liouville operators, but there are certainly paths forward for making those higher order Liouville operators. And the signal valued reproduced kernel Hilbert space is sufficient for defining all of those operators that come after that point. So what's significant here is if you take a look at those eigenfunctions, the only place that you need to take a numerical derivative is at the origin. And if you already know what the initial conditions for your system are, you don't even have to take a numerical derivative there. So this allows us to dodge the entire state augmentation and numerical derivatives along the entire trajectory in a very, very clean way. And what's even more significant is that when you make these finite rank representations and you go through and you do all the computational mechanics, you'll notice that you never actually need to touch the range Hilbert space.
All right, let me tell you the good news. We don't need the monitor. Oh!
And so what's really cool is that you can just forget about the range Hilbert space, and you just need to deal with the Hilbert space that you constructed this out of using your canonical representation. Now, the manuscript for this is posted up on Archive, and I invite you guys to go check it out. We have the theory up there, and later on we're going to update it once we have the computational bits. We still need to add bits on the higher order Liouville operators and how to find them, but we'll have that up in a few weeks. So as I wrap up here, I would like to say that if you like this video, I have actually been having a lot of fun doing online classes, and I do everything asynchronously and post them to YouTube. So I'm teaching a data-driven methods and dynamical systems class right now. And right now we are heading into the operator theory methods that I just talked about. So if you want to hear more extended discussions and much more detailed technical analysis of all the things that I talked about, you should go ahead and look up my YouTube channel. And yeah, we have fun, and yeah, I encourage you to subscribe. Okay, so with that, good night.